think that's probably so that turns into a lead halide perovskite structure when you start baking that on. And then you dissolve some spiral into apparently it's like $1,000 a gram. What? Yeah.
What? Jesus.
It's okay.
When you start trying to make a correlation between CO2 and mores?
Yeah, you just drop past that.
What?
Let the solution
Oh my gosh.
evaporate.
So maybe a more relevant question.
My seventh
on
grade.
at this point.
Started discussing waters. And
Up to like 20%.
every
I'm probably not
conversation
going
we
to
had
actually
yesterday was very like,
Intellectual.
yeah, surprisingly
What's the
so.
maximum?
But so we got on the topic of wars, and I was like, whatever, I don't want to do wars.
It's gotta be like less than 25%.
And how every
I mean,
war,
I
like,
mean, to be honest,
was not
I mean,
connected between every war. So if you think like every war is and all this stuff, yada yada yada. And
what can I steal from the sun?
I mean, they're pretty small, so not much.
But quantifiable?
We missed it.
Yeah,
If I get one that works.
Right, yeah, it'll be measurable on a volt.
Well, he ended out a lot of stuff that day.
Right now, this one is just not working at all. I'm pretty sure that I should have put the aluminum on this last slide.
I mean,
I'm pretty sure I just short circuited the whole thing. So
every single war during the medieval ages was connected. Because they were
And then
either religious or they
this
wanted more
one, I
land.
can get
And
like
one
a
country
couple
got
of
too much land, they
100%
fought against.
and no current.
Also, one of my seventh graders came
What
up to me
range does
yesterday
it absorb?
and said, I bet I have a secret to tell you. I was like, okay, what is it?
Is it
I
your favorite
can't
soup?
get the current out of it, so I have it.
Do not disclose.
Well,
I'm just curious.
first, yeah. She's
What
like,
would
I
it
guess
be
maybe
like?
not
Is it dye?
really, but sure.
Yeah, the perovskite is technically like the dye.
Alright, I'd say so.
That's,
Hello, or is it-
it's, well, that's like the, that methyl solution as well. So I didn't really take this one on long enough for how to for whatever. This one kind of doesn't really work. I get a couple millivolts out of it, but no current. This one doesn't work at all. I'm pretty sure I should have put the aluminum onto the clean glass slides and then sandwiched them. So I'm pretty sure I just short circuited the whole thing. So I got to start over on this one.
Okay. And you left the clean areas on both sides at the side, right?
Yeah.
And you didn't flip it in the wrong side.
At least I hope not. I can
When I was doing it, it started working, more or less working maybe on the 5th attempt.
Yeah.
So if it doesn't work on the second, it's okay. Well, thank you for keeping investing your time into physical chemistry. In case you are watching it on a recording, or in case you were missing a lot of class, it is not yet late to pick up. There are 3 meetings who can compensate almost the whole course or substantial part of it in terms of grades. There is tonight lab, the meeting on coming Friday, and the presentations in one Friday later. So those are most important parts as you may have realized. If I fail to return to someone who works in the reasonable time, I will just assign the highest grade. So do not worry too much if I didn't. So it's a little motivation for me to finish them. So there will be no class today in a sense of regular class, or no new material. First. Second, I will talk about our research projects from organizational, administrative part, requirement, how to organize the written reports. And I will present it in upside down fashion. So I will start from assuming that everything is ready, all research is done, and just how to put it together, and then I will develop back to technical details. What else? So I may have distributed these handouts half a year ago. but if I can distribute it once again and you do not need to return, if you do not need, just file them aside. If you want, you can take them with you. It is what was done in a similar class by other students. So the projects do not coincide, but the approaches and style could be very similar. So you, so in scientific activity, it is what people do every time: read what others have written, get inspired, and write it over again about their own systems. So it is not cheating. It is not illegal copying. It is getting inspired by works of others and standing on the shoulders of giants, or maybe not giants, depending on whose works you are reading. Also, here's a summary of what I will be presenting. So I copied a couple of pages that I like it most for my presentation. Today, it finally it is able to record the front camera. See? I was not able to do it previously, and now probably does. Okay, so you are there.
I was gonna say the people that you should look at.
Huh?
You should have it zoomed in on the people that should be looking at.
Okay, now it is recording of attendance. If I want another camera, everything works. It's a lucky day today. Do you think we are the first in the humankind history who write research reports? Do you think we are the first in the humankind history who do research presentations? Okay, even less specific, we are not the first who are writing generally reports on arbitrary subject, and we are not first who do presentations. So it's activity of humans for not centuries, but several millennia. And through this long history, there were developments of standard approaches that do not affect the contents of what you're doing. So you, as a creative people, you do whatever you like or do not like in your project, but in a way to perform better scientific communications. And we cannot, maybe unfortunately, to do science just I hide in a cave, do science for myself, develop equations, get happy. It's by the nature of this activity, it's all communications through other people, testing if they like or do not like it, if they accept proofs or try to prove it wrong. So there were several thinkers in the ancient times who were giving instructions, suggestions, what to do when you need to do presentations. So one of them is Aristotle from Greek, and he was mostly, I don't have much of education in classics, it's all from Wikipedia. So that you can read yourself. So this Aristotle, he is giving more ideas of how to present things in public. so that you do your creative work, then you think about how to present them after your research project is done. Then you organize it. It is basically main part in writing reports, so how you put it on paper. And then some things, how to do presentations, how to change tone. I don't think it is super important, but who knows. And there is a thing that is completely obsolete, because we have our electronic gadgets with all things recorded, so we can have zero memory, and we will not suffer from it. So it is too general. And there was another thinker in ancient times who, as always, there is a difference between Greek and Latin approaches. So Greek is more general philosophical and Roman is more practical. So not where to go, but upon the purpose has been determined, how to reach it in the quickest way. And there was a person who was giving public speeches for money or for free, I don't know, for any cases, to convince people to follow some idea. And he summarized, so the name of Cicero and the summary of the best talk, in his opinion, is to teach, entertain, and motivate. If any of you have classical education, you may try to read it. Like dilectere, tacere, movere. So making people entertain, give something new that they to satisfy curiosity, and then if you are speaking, it means you want to motivate people to do something. If it is in the court, to take this right decision. If it is on the market, to buy your product. If it is in a science, to believe that your results are correct. And this thinker left detailed instructions of an ideal manuscript, ideal written report. You will see that some of the statements are very similar to what we do today, what you were doing in the past, what you will do in the next few days, and some things are different. So he suggested to compose the manuscript of 6 sections. So the exordium, which is like very brief abstract of what you do, then narratio, which is like telling what other people are doing and giving general introduction what was done before you. Then summary of what you have done, even before you go to the body of your actual research in our case, or I don't know, lawsuit in other cases. So he called it the divisio, and then the proof of case, confirmatio, which in his splitting of the manuscripts took maybe 10% of the whole story. In the modern science, in tradition of scientific manuscripts, typically, this is the major part. This may take like 70% rather than 10. But in ancient times, when people were doing not in a rush, it was not much in actual material, like tables, figures, equations, data, but more explaining who needs it, what is the open problem, and then next to discussing. Do I believe that it is correct or not? Or, so he called it confutatio. We can call it discussion. When a person tries to convince that it is correct, or playing a dirty trick, asking who is against this statement and then trying to put down this person by all possible means. So, like, well, I'm not telling you to write in the report like you write. Here were my results. Do you believe them? If no, you're stupid. it's how I understand ancient rhetoric. Maybe it was a little more advanced. And then the peroration, which is conclusion of everything you did before, and then trying to do some energetic statement to induce positive feelings toward the case or the client, or negative feelings against anyone who doesn't accept this result. Right? So you got general idea what is in written report. Instructor, do you believe that my work is the best of the best? If no, so more practically to what you plan to do. We do less of the discussion, less of the introduction, although any research papers included, just in smaller percent. So you may explain what is the system of your interest, and there was a percentage of your free will choice. So you may explain why you have chosen one or another problem. For this problem, you can explain what is not clear. Like, if you want to research it, it means that for the whole world, or at least for yourself, something was not clear about the system. And you may state your open questions. What was not clear? And then, even before, so this idea came from National Science Foundation. They requested from anyone who wanted money from them. So even before you start any actual scientific research, you may provide hypothetical answer to your question. So guess, to your best educated guess, what could be the answer to this open question. And then you tell, just state that your approaches to your best belief may support this answer. Typically, people write it after all results are completed. So it is a little bit not straight, hypocritical. Like, I don't know what will be the answer, but for those of you who didn't started doing actual calculations, it will be completely truth. If you start writing before you do research. And for a reader who read the manuscript, it looks in a straight logic. Here's the question, here's a possible answer, and then you'll try to prove it. Now, methods. If you study the same problem again and again several years, you can skip the methods or just read my previous papers. But sometimes it is audience doesn't buy it, so you need to provide some minimal details that would help your followers, if any, to reproduce the results. So maybe some people believe that you do congenial work and they just want to do the same. Maybe some engineering people or pharmacy people want to synthesize the same chemical and repeat it. Or maybe some critical reviewer wants to prove that you are wrong and repeat the same experiment in computer simulation or in lab. So you need to play fair game and give enough details to reproduce. If it is computational and theoretical simulation, it means that you give enough equations for the methods. Results and discussions. So it is what Cicero noticed as confirmative. So like confirm that your whatever you want to prove is correct. So you give, in our simplified case, you give figures and tables, and basically explain what and why. In the figure 1 shows this because we do not have much time to do. So basically, if you are in a rush and if the length of the manuscript and your time are limited, you just put figures and explain them one by one. Right? If you are so productive, which can be the case that you have generated more figures than you can fit in a short report, and you do not feel comfortable to leave them away. There are two ways. If it is a true scientific paper, you provide electronic supporting information, and you put all garbage that is not good enough for main paper. Here, we will, in these examples, you do not see supporting information section. So you either delete it or compose multi-panel figures. Panel A, panel B, panel C. But it is only in the case if you suddenly realize that you generated too much data. For most of us, in the limited time, it will be not the case. And what to write in conclusions? Refer back to the question and hypothetical answer, and write, oh, what a surprise! My initial hypothesis was proved. It is a great discovery, right? So it's a standard step, but when a reviewer reads it, it looks much easier and much logical to read. So you may be boring and write, we did this, we found this, and maybe it is interesting. But if you loop it logically, it will read much easier, much more pleasant. And again, based on Cicero, you want to convince reader or viewer or editor that it is valuable and trustable. So what impact your work? So if you, whatever you design a drug or design a catalyst for whatever, catalytic converter, without my work, all cars will still stop. Without my drug, people will not live long enough. Or without this equation, we all become ignorant. I'm exaggerating. Conclusions with impact. So, I'm done with general. No, not done. Impact. This is completely challenging. Your intellectual development is 100 times above this figure. But as long as you develop in your educational path, no matter what it will be your next forking, branching, like industry, education, research, you are, with your development, you become more and more specialized in some area of knowledge. And your knowledge in some areas depart from the pool of common sense in a good way. And if you want to convince someone who is not from your team that you are doing something valuable, you need to roll back and explain what you are doing in a simple language and convert it in the very clear explanation who needs it. So I hate this activity, but I just learned that it has to be done all the time. So if you are doing research and you want to pull money from government who pulls money from taxpayers, you need to convince that you are not just satisfying your own curiosity, but doing something useful for the society. In most cases, it is truly so, even if you do not realize it. But in some cases, not. But anyway, you need to provide arguments. So, standard way, immediate way. After you're doing publications, there are people in maybe engineering departments who scroll through, design devices based on your materials or protocols or new chemicals, synthetic protocols. Patent, get the benefits of bringing it more to closer to production cycle, and then it goes to industry and gives, like, if you do solar panels, you provide everyone with almost free energy. If you do electronics, you help everyone to have cell phones. And there are similar tracks for drugs and I don't know, security and some other applications. Another path how if nothing of this applies, but you really want to complete your research and convince readers that you're doing something valuable, through this curricular activity, through this research, there is a development of next generation of scientists and teachers who, through education, will serve citizens, or through generational workforce will enter industry. So it is a last resort if you do not find other arguments.
You're a last resort.
But maybe if your plans of professional activity is in this area, you think that it is a first thing, right? No. But it is very adequate, correct, and normal to mention it, even in the short reports. Yeah, discussion is natural part. So this thing is already distributed. So practically, how do we organize research? And I'm too wordy here. It is excessive information. In fact, what you do is simpler and quicker. So I want to believe that this part is done by me. So before doing research, you plan it a little bit. So you select potentials, which we spent like 2 weeks to vote and design for those who were attending evening sessions. And then there is a concept of activation energy, which is very, very general for majority of reactions. If a chemical is stable, it means it will not decompose spontaneously, which means to decompose it or to launch a reaction, one needs to provide energy, for example, by heating. And this activation energy in the potential, you can just estimate it as a from initial to the maximal barrier will be your estimate of energy. And then you can set up initial conditions, at least for wave packet, which should be localized in a part of the potential that corresponds to reactant. And then you are done to start. Assuming that you have debugged the code and you are sure that it works. So the code is not the goal. The code is instrument. If something is not working, I'll try as much as I can to help. So your actual research starts after this slide. So there will be, after this, 2 more slides, but they will be more on logically connecting and preparing for presentation and for report. This is the only slide about the actual research, about practical work. So, and actual work is only this step, or maybe this 3 steps. This is also sort of preparation. So make sure that you have to assess the yield of reaction in a single run and the rate of reaction in a single run. So for the yield of reaction, you can glance through this printouts. You just integrate left part of the cell, right part of the cell. Probability there at a given time will be reactant and product. Okay? And if you measure probability that wave packet converted to the product 100% by the end of your simulation cycle, then it is 100% yield reaction. In these approximations, in this simulation. The rate can be computed in 2 ways. One, if you just do derivative of product formation probability over time, it will be rate. But this one will be very noisy and it will depend on time. Another one is to try to fit your dependence of product formation to linear, to the exponential. And this is easy. Even if you do not have it, it is maybe 5 minutes exercise. So, actual research, only these 3 points. Before, in everything we did in class, we didn't speak out the word temperature, because it is not statistics, it is not thermodynamics, but even if you do not pronounce the word temperature, temperature does exist. So for you cannot decline it, its presence, which means that whatever objects we deal with, they have non-zero kinetic energy and non-zero momentum. So for our, in a very, very rough approximation, we can assume that the reactant, the reaction coordinate, or whatever, maybe electron, the system has non-zero momentum that we can model by assigning P naught in the code for the Gaussian wave packet. Of course, if you want to be very rigorous, we need to do ensemble average where this P naught is directed to left, right, and some other directions in multidimensional. You have a sample over random directions of the momentum. But as a very rough approximation, just moving towards barrier with different values of momentum is already qualitatively correct approach. This will work and give reasonable results that you would enjoy. So you do set up the initial value of momentum. Run your code once. Record, maybe not for the paper initially, only for yourself, the product formation trajectory, the rate and yield. Enjoy it, and then record it, and then select another value of initial momentum and repeat. How do you select initial values of momentum? And what is our hypothesis that we want to prove right or wrong? Some of you may have already designed serious scientific questions. What I'm providing is a little learning curve question, but it is interesting to check. It will work in one case and will work not in another. So the momentum that we set up in the wave packet determines kinetic energy. And if this kinetic energy is equal or higher than your estimate of activation energy, reaction should go completely, 100%. If it is less, it shouldn't go at all. Right? So this is the statement that we can prove right or wrong. Of course, it will not be 100% fulfilled. For example, if it is, if the barrier is not only high but wide, preventing tunneling, it will change the difference. If you're, if you including electric field, you need to add some additional thinking. This would work much better for heavy nucleus and molecules. For electron, this thing sometimes works, sometimes not. So it's interesting to check. But from this generalized question, from this generalized problem, we may select such values of momentum that range in the vicinity of your estimate of activation energy. So starting no temperature, no activation, no kinetic energy, and then twice as much compared to activation energy. So that you explore all ranges being lower and being higher. And some of you may decide, I want to optimize my effort. I'll do a cycle when the computer will range for all values from 0 to 2. I run it once, relax, and then collect data. It's correct, it's practical, but nothing works from the first time. So it's better to do just change value, run, record. Change value, run, record. It's not very intellectual, but the benefit of such obsolete approach is that you may tweak the step size. If you see that you change it by so much, and nothing changes, you can next step making it larger. Okay. And also, energy is square of momentum. So you need the momentum needs, if you want to equally space points in energy, the values of momentum should be spaced as square root of this energy. So repeat and record. I will return here, but let me show here. Yes. So you may arrange a table and record value of momentum, kinetic energy, yield of reaction, rate of transfer. Just fill the table. As soon as you fill the table, your research is kind of done. The rest are technical details. So, like running the code about 10 times, recording this data is very much sufficient for successful completion of the research. The rest is convincing your readers that you're right and preparing colorful figures to make it easier to read compared to boring text. Table. Returning back. Okay. So upon collection of data, you start analyzing, which is, again, your creative free choice. For some systems, one point of analysis is more important, for another is another. So you can verbally analyze whether you see what you expect, that there is no reaction in kinetic energy than less, and it is 100% if it is higher. If you run the code even humble 10 times, it will be a huge amount of graphical information. You cannot show all of it in 4 pages of your report. So you select most representative example of either wave packet shape or population as function of time. So even in this small learning project, we hit the big data problem. You cannot, human cannot look and analyze and communicate to other humans too much information. We need to summarize and condense what you find. So representative examples and verbal explanation. Well, if you want to make connection to real life, you may convert it from your results from atomic units to something more useful, like inverse nanoseconds or time of reaction in nanoseconds. Or if you do differential rate, you may see that reaction rate changes in time. Also, I would answer that this question C4 has a trivial answer, that kinetic total energy shouldn't change. But if you are coming from region with different potential, there is a conversion of kinetic to potential, potential to convert kinetic, and you may see increase or decrease of the overall kinetic energy. And if you see overall increase of kinetic energy, it means that your system is heating up. It is a combustion reaction with release of heat. Right? So even this small code that you're practicing may give you answers on such ambitious questions. Philosophically, yes. Practically, no. We do not have, I will not discuss in much details, it is just to launch your imagination. But if you take a classical harmonic oscillator, prepare it, let it move, after some time it will return into exactly initial condition, initial state. Is it possible that quantum state evolve, and then return into the initial state? If you have nothing to do with my answer, but maybe you'll be too busy to analyze it. Approximations. We are not doing exact science, exact calculations, and exact computation, exact calculation is not possible. Any calculation has a lot of approximations. It's any theoretical approach is an art of browsing in the space of approximations. You cannot take into account all degrees of freedom, all particles. You always reduce your system, and you may tell what you did neglect. And then you can share your, again, everything is optional. It's too much to be monitored. You may say how nice this method is, or how bad it is, and how you would like to improve it, if you would get that chance. This is something that we will do in a week from now, next Wednesday, in preparation of the oral presentations. So taking one or a few representative dynamics pictures, converting them into YouTube movies, uploading and sending the link to this YouTube. Why? You see in this booklets that for such of readers who will see it electronically on the first page with contents, it is much easier to just watch the movie than to read the whole composition, right? And then in the very, very last part of summary, you can tell your experience whether, what is the impact. So you can share your vision of impact on the society, on industry, pharmacy, and maybe to your own pleasure or opposite. It didn't teach me scientific computation. It has nothing impact on research strategy. It doesn't help my industry career, and it will not help me to become a teacher. Well, I hope opposite. So here is the graphical summary of what we discussed. So you select a model, which means you choose a potential with the rest of the code has been provided. And then you go to path, and then you compare them. So simplest path is just you look on the potential, identify value of activation energy, and it will be your reference point. Another path, you select momentum, run dynamics, compute rate, repeat, again, and then from analysis of the data of these potentials, there is an equation that you may have seen in the chemistry 151 or whatever you like, freshman chemistry, or if you didn't, we'll cover it. It's a way how to convert table of values of temperature and values of constant reaction rate into activation energy. So it is one of the standard ways to summarize data in chemistry. It's Arrhenius plot. And from here, we will estimate the activation energy and compare it with the reference point. Program maximum. Even if you do not get to this, do not panic. It is a wish list. What else? Again, a little extensive list of possible figures. 4 pages would not fit 7 figures. I know. So you can either skip some of them or fit them into multi-panel. It's just general idea, because sometimes input is helpful. Maybe schematic explanation of what is your system. You can sketch it or take from Wikipedia, or if there is an atomistic modeling, take some CHEM364. Potential and initial wave packet, which will help a reader to read. This is very optional. If you have potential, you can always find its eigenstates and plot them. Same thing as we did for box, oscillator, like energy, eigenstate. Last thing, most likely no one of us will have time for this. Examples of typical dynamics. It is what I've told. We run it for 10 times, but we can show only one in figure. Otherwise, it will pop up too much length. Population as function of time. Again, one example. And then rate of reaction as function of either momentum or kinetic energy or temperature or inverse temperature, or both. As a looking forward, I'm giving a hint that if you plot it as logarithm of rate versus inverse temperature, it would be most representative. The picture would look not in a strange way, but if it is a well-defined system, it will be a linear dependence. And there are, I wouldn't say theorem, it wasn't proven, but practically it works for very many cases. So, I hope to see you tonight at 5. But you can do it at home at your laptops if you have installed that. What I do care about, please write 4 pages reports and bring them next time in class. Please print 3 copies. Okay? And sometimes I do not pay attention to details, and I imagine myself in your place. Okay, meeting is done. I will stay here in case there are some questions.
Did you hear about the abstract algebra test?
Yeah, average is 55.
Yeah.
You got a freaking 93.
Yeah. About to hear about how disappointed Boyd is, the entire class.
Right. Really the entire class? You got a 90?
93. Yeah. But the average and the median are both.
But is he really disappointed in the entire class?
Not the entire class.
Most of it.